A malicious package was sitting inside the PyTorch Lightning dependency tree, executing code on install, and a non-trivial number of ML training pipelines pulled it in before anyone noticed. That is the situation. Let's talk about what actually happened, what the attacker did, and what you need to do right now if PyTorch Lightning is anywhere in your stack. The discovery came from SemGrep's security research team. The malware was themed around Dune, specifically the sandworm Shai Hulud, which is either a calling card or someone having a bit of fun while doing something genuinely harmful. The naming doesn't matter operationally. What matters is the mechanism. The attack was a dependency confusion or type-squatting vector, unclear from the reporting exactly which variant, but the payload was embedded in a package that PyTorch Lightning pulled intransitively. That means you didn't have to explicitly declare the bad package in your requirements file. Your direct dependency did it for you. This is the part that makes supply chain attacks so effective and so underreported in postmortems. Engineers audit their first-level dependencies, they do not audit the full resolve tree, and attackers know this. The malicious package executed on install, not on import, on install. That distinction is critical. The moment pip resolves and installs the package, in your CI runner, in your Docker build, in your local virtualenv, the payload runs. You do not have to call a single function. You do not have to import anything. The active installation is the trigger. This is a well-understood attack pattern at this point, but it keeps working because the Python packaging ecosystem has no mandatory code signing, no verified publisher model by default, and pip install is treated as a safe operation by basically every CI pipeline ever written. What did the payload do? Based on the SemGrep write-up, it had data exfiltration behavior. Specifically, it was going after environment variables and credentials. If you are running PyTorch Lightning in a training environment, and a lot of teams are, because it is a legitimate, widely used library for structuring PyTorch training loops, you may have cloud credentials, API keys, weights and biases tokens, Hugging Face tokens, or internal service credentials sitting in your environment at build time. Those are exactly what this kind of malware harvests. It sends them out over the network to an attacker-controlled endpoint. The severity here is not theoretical. If your CI environment has AWS credentials with any meaningful IAM permissions, and that environment ran a pip install that pulled this package, you should treat those credentials as compromised. Rotate them. Check your CloudTrail logs or equivalent. Look for API calls that don't match your normal patterns in the window after the affected builds ran. Now let's talk about PyTorch Lightning specifically, because there's some important context. PyTorch Lightning is maintained by Lightning AI. It has a large install base in the ML engineering community. It abstracts a lot of the boilerplate around PyTorch training, handles distributed training setup, checkpointing, logging integrations. It is not a toy library. It has millions of downloads per month on PyPI. That scale is exactly why it is a target. Attackers do not go after niche packages with 300 downloads a week. They go after the packages that are in the dependency graphs of hundreds of thousands of projects. The specific attack surface here is the transitive dependency graph. PyTorch Lightning has a substantial set of dependencies. Some of those are optional extras you install with bracket syntax, things like the various logger integrations, cloud storage backends, and so on. The more optional dependencies a package has, the larger the attack surface, because each of those subpackages is a potential injection point. SemGrep's research found the malicious package somewhere in that graph. The exact package name and version range should be in their full write-up, and you should go read it directly rather than relying on any summary including this one, because the specific identifiers are what you need for your audit. Here is what an actual response looks like, step by step. First, identify every environment where PyTorch Lightning is installed. That includes production inference servers if you serve models, training clusters, CI/CD runners, developer laptops, and any Docker images you have cached or pushed to a registry. All of them. Second, for each of those environments, pull the full resolved dependency list, not your requirements. TXT, the actual installed packages. Run pip list or pip freeze inside the environment and compare against the indicators of compromise from the SemGrep report. If you use pip audit or a tool like Safety, run it now. If you do not have those tools in your pipeline, this is a reasonable time to add them. Third, check your CI logs. Look for outbound network connections during pip install steps that go anywhere unexpected. If your CI runners are locked down with egress filtering, you may have already blocked the exfiltration, but you still need to know if the package was installed, because the install itself is evidence of exposure. Fourth, if you find evidence of the package having been installed, rotate every secret that was in the environment at that time. Do not try to reason about whether the specific exfiltration call succeeded. Assume it did and rotate. The cost of rotating credentials is much lower than the cost of an account compromise. Fifth, pin your dependencies. I know this is advice that has been given approximately 10,000 times, and the response is usually, yes, we should do that. But pinning your full resolved dependency tree using a lock file, using pipcompile from piptools, using Poetry's lock file, whatever your toolchain supports, means that a newly published malicious version of a transitive dependency does not silently enter your build. It is not a complete defense, because the malicious package could have been present at the time you generated your lock file, but it dramatically reduces your exposure window. There is a broader point worth making about the ML tooling ecosystem specifically. The machine learning Python ecosystem has grown extremely fast, and a lot of the security practices that the broader Python community has slowly adopted, dependency pinning, hash verification, private package mirrors, egress-restricted build environments, are not consistently applied in ML workflows. Training pipelines are often run by researchers who are optimizing for iteration speed, not operational security. The environments are often ephemeral cloud instances with broad IAM permissions, because attaching the right scoped role to a spot instance fleet is friction. The combination of broad credentials, fast-moving dependency graphs, and less security-hardened workflows makes ML infrastructure a high-value target. This attack is consistent with that pattern, and it will not be the last one. One thing that is unclear from the reporting is the timeline, specifically how long the malicious package was available before detection, and whether PyPI has removed it at this point. You should verify the current status directly with the semgrep write-up and the PyPI page for the specific package. Do not assume it has been taken down just because the story is public. The real takeaway here is operational. Treat your ML training environment the same way you treat your production deployment environment from a secrets hygiene perspective. If you would not put a long-lived admin credential in a production API server's environment without scoping and rotation policies, do not put it in a training job. Use short-lived credentials where your cloud provider supports them. Restrict egress from build and training environments at the network level, and run pip audit or an equivalent on every environment that touches external packages on every build, not as a one-time audit, as a recurring step in your pipeline.